let me get organized here. I would like to start actually by, well, sharing my screen, obviously, and then just as in some of the classes that I teach, I thought that we would start with a warm-up question so that some of you might show that you remember something that we already covered yesterday. And I will post the link to the poll once again in the chat momentarily to everyone. There we go. All right. And then some of you have likely already started to read. We can read through this together. So there are a couple of statements that are related to material we looked over yesterday, and I'm looking for one of those statements that might be wrong. So A says critical current and Josephson energy are proportional to each other. B claims that if we reinterpret the circuit Hamiltonian for the transpon as describing a fictitious particle, then the mass of that particle is proportional to 1 over the charging energy. C says for a quantum circuit, voltage and charge play the roles of generalized coordinate and conjugate momentum. And D says since the transpon Hamiltonian only involves 2 energy scales, namely EJ and EC, and no other parameters, the different regimes of this circuit can be classified by considering the ratio of EJ over EC. So I'll give you a moment to think, and you can start putting in your choice of A, B, C, or D into that poll. And I'm just bear with me. I'm going to shift my browser window over where it doesn't disturb you. There we go. Let's see. 3 people have voted. How many do we have actually? Where's my participant window? There, 33. All right, we can get a few more. Everybody has to have an opinion. You have to play the game. 8. Okay, let's do a little bit more. 11. Oh, this is a slow day. Last chance. Good. I'll take the 12, although it's sort of scary that there are so many among you who don't want to vote, or perhaps you've stepped away from the computer and you're just not there. So let's see what the results show. Results are in, and results are very mixed. So nobody's unsure. That's great. But we have a pretty even distribution among all A, B, C, and D. So that, I think, tells me that there's a little bit of repetition and redundancy that might be in order. So critical current and Josephson energy, we briefly touched on that yesterday, and I can bring up the lecture notes from then. That would be here. Right, so in this place, we computed the energy associated with the Josephson junction. Here's the expression that comes directly out of the computation. And then we said that, well, we simplify that in by introducing a name for this. It has units of energy, obviously, and that is the Josephson energy. So EJ and the critical current I sub C are proportional. That's a correct statement. Let's return to choice B. If we reinterpret the transpon Hamiltonian as describing a fictitious particle, then the mass is proportional to 1 over the charging energy. That is also a correct statement. So let me try and convince you of that. Right, how does the transpon Hamiltonian, what does it look like? It starts with minus 4 EC d squared by d phi squared, and then there's the potential energy term, which actually comes with a minus EJ cosine phi, right? And what you're used to for a particle is for this coefficient up front, you probably expect that to be something like h bar squared divided by 2m, right? That's what you would see there. And since the m is in the denominator, the c is in the numerator, they are one is proportional to the reciprocal of the other. Okay. Now, C, for a quantum circuit, voltage and charge play the roles of generalized coordinate and conjugate momentum. I could ask what you thought about that, but I'll try and make it efficient. So this is the wrong statement. We actually agreed to introduce a so-called generalized flux as our generalized coordinate, and that was the time integral of a voltage. And so it was charge and the generalized flux that were conjugate to each other. In fact, one thing to keep in mind is if you have whatever generalized coordinate you work with and you have determined the conjugate momentum, then the product must have dimensions of an action, right? Because the commutator must be something related to h bar. And so that doesn't work out for voltage and charge. And then last but not least, claim was that Transpon Hamiltonian only has two energy scales. Looking at this Hamiltonian up here, right, that is indeed the case. And if I just divide, I'm going to measure all my energies in, say, units of EC, then the EC drops out on, in the first term, and we see that the entire physics is determined by this ratio of EJ over EC. Good. Are there questions about that? I really do encourage you to, I'm fine if you just speak up. I like things to be a little bit interactive. So if you feel brave enough, then interrupt me whenever you like, because obviously these lectures are for you, not really for me, and I want you to get the most out of them. All right. So
so maybe on this, I think they cannot unmute themselves.
I see.
Sure. Yeah. So if you have questions, just raise your hand and I will.
Yes, everybody can unmute him or herself.
Okay.
So
okay, sorry about that. Okay.
Okay, good. Yeah, whatever works. I know some people don't feel comfortable speaking up. I encourage you to do that if Zoom allows you to, but you can also post or raise your hand. That's all of that is fine. Okay, good. So let's pick this up where we left yesterday and had to pause. So we had just started talking about decoherence. We learned a little bit about the transpon, but the question was, well, how good is it? And good for a qubit certainly has to do with, well, for how long does the qubit stay quantum mechanical rather than turn into something that we could even describe classically. And so the two keywords that we will get to are depolarization. In some simpler cases, you would just call it relaxation, and pure dephasing on the other hand. Great. Already showed this slide and talked a little bit about, qubit is not alone in the world. There are a variety of noise channels that can be detrimental and affect the coherence of the qubit. And so as I promised, we'll try and distinguish different kinds of decoherence. So let's do that. The first one is, indeed, I'm just going to talk about relaxation. I can say something about why depolarization is the more general term, but let's imagine that we've initialized the qubit in the excited state. Sylvia, can you confirm that you can see my cursor? Is it visible? Excellent, thank you. So qubit is initialized in the excited state, and what you will observe usually is that after some random time, this excitation will disappear. So the qubit will emit perhaps a photon, and it will jump down into the ground state. So this happens at random times, that's correct, but there's a distribution, and the mean time, that is what we call T1. That's our relaxation time. Depolarization just refers to the fact that if temperature is not zero, then you don't you have the opposite process as well, right? You might start in the ground state and spontaneously jump upwards into the excited state. And if that is something you have to consider, then relaxation doesn't seem a great word. So depolarization is what people call that. Okay. And so there's a certain rate associated with that, right? 1 over T1 is this depolarization or relaxation rate. And how do we know about it? How can we calculate it? I'm just giving an expression here, and I'm not going to show the derivation. There's a nice derivation, I believe, in a somewhat older review of modern physics by Steve Girvin and Ash Clark that talks about quantum noise. But all that we need to understand right now is that essentially we treat the coupling between the qubit and the environment with perturbation theory. So we can use something like Fermi's golden rule and actually get the expression for this rate into a form that is, there may be some factor up front that is constant, but the important pieces here are there's a transition matrix element, right? The qubit couples with some operator A to the environment, and we have to take the matrix element of A with respect to the two states that are involved, the mod square of that. And then the other thing that matters is, well, what does our noise look like? The strength of the noise may vary with frequency, right? That is described by the noise spectral density S of omega. And for depolarization, the frequency that matters is the qubit frequency, right? Because that is the energy scale that is involved in this very process. Good. So that is depolarization and T1. Next up is pure dephasing. So pure dephasing that entails processes where the qubit actually doesn't really exchange energy with the environment. So it's a little bit different. And what takes place is you have slow variations of the qubit energy splitting. So there's some noise that influences that qubit splitting and leads to fluctuations of the qubit energy. And if you recall what evolution under the time-dependent Schrodinger equation does to a state, then you may recall that an initial state written as some complex coefficient alpha times 0 plus beta 1, that is going to turn into a state where you have a dynamical phase factor. I've made things simple here in a way that, the zero state for me has zero energy, and then it's just the difference of the two energies that appears directly associated with the second term. All right, but now imagine that this qubit energy splitting, which I'm not completely consistent here. So omega q, h bar omega q is the same as E01. I hope you can forgive me for inconsistent notation here. So this phase factor, right, is going to start fluctuating itself because the E01, the qubit energy varies. And so in a somewhat hand-wavy way, what I'm writing down here is that you get a state that in a sense has a random phase. And that is certainly not good for quantum computing. We can make this a little bit more rigorous. So those of you who are familiar with density matrices, in that case, the statement is that what pure dephasing does is it eliminates the off-diagonal elements in the density matrix and reduces your quantum state to a mixed state in the general case. So that obviously is not good for quantum computing either. We need to work with superpositions. We need entanglement along the way, and pure dephasing doesn't do any good when it comes to that. And the rate associated with that is 1 over t phi. So t sub phi is my pure dephasing time, and that expression is also very simple. It involves the derivative of the qubit frequency with respect to, well, I'm calling it lambda here. It's whatever you want to call this fluctuating parameter that affects your qubit frequency. So we take the derivative, and the derivative really just means, well, how much does the 0-1 splitting change as this quantity fluctuates? So it's the linear sensitivity to noise. And then the noise power spectrum, again, matters, but in this case, we're talking about slow fluctuations of the qubit frequency. And so this time S is evaluated at 0 frequency. Good. I think, yeah, I did have a follow-up question on that. So let's see. If you consider these expressions above, which of the following statements is wrong? A says 1 over f noise with that 1 over f or 1 over omega dependence is particularly bad for dephasing. B says suppressing the noise at the qubit frequency increases T1. C says at so-called sweet spots where the first derivative of omega q with respect to the noise parameter vanishes, both T1 and T5 are enhanced. And D says the approximation above would predict infinite T sub phi at sweet spots. All right, don't vote yet. I think I have to clear the previous results. All right, now the poll should be ready. Oh, very good. And while you vote, I do see that there was a question in the chat. Luca would like an example of a process that causes dephasing. Sure. So one thing that causes dephasing, I mean, I can answer this in terms of what physical process, or I can answer this in terms of, you know, what's the operator that couples to the bath. I'll try and do both real quick. So suppose that you have a qubit described just as a two-level system with, you know, its axis is the z-axis. So the pure qubit Hamiltonian is just 1/2 omega q sigma z. If the coupling to the bath is also through sigma z, then that coupling is not going to lead to energy exchange. There's no dissipation. And so that coupling would only cause pure dephasing. A good physical example perhaps would be if you have a qubit that is coupled to a resonator, and the resonator is subject to photon shot noise. So you know, let's say there's a non-zero temperature and photons enter and exit the resonator, then that will cause pure dephasing for the qubit, because the qubit frequency is dependent on the number of photons in the resonator. That's something that we'll see along the way. I think for now, if you're not familiar with that, you'll have to just believe me, but there are indeed these processes that just correspond to pure dephasing. All right, that was that question. And now let's see how many people have voted. 14. All right, I'll take that and we'll look at results, and results are in. And most people think that C is wrong, and you are right. The statement should be that at sweet spots, T5 is enhanced, but T1 actually doesn't care very much about that derivative. And so the T1 would have to be dropped. Now, I do see that there were a couple of people who voted for A. So 1 over F noise is indeed particularly bad for dephasing, because the noise spectral density, right, actually diverges if I take this 1 over F completely seriously. In most cases, we assume that there's some cutoff along the way, but 1 over F is as bad as it can get if you try to really plug in zero frequency, right? Good. Questions about that? No questions. All right, moving on. One quick comment on what have people actually done over the years to deal with this problem, to increase coherence of qubits, which is really, really important in order to move forward with building larger and reliable quantum processors that hopefully one day will be quantum error corrected and fault tolerant, so that we can really scale things up. So there are different strategies. Number one is sort of the strategy that you say, well, there is all this noise. I don't know how to get rid of it, or maybe it's really hard to get rid of. And so all I can do is I can protect myself from the noise. I can try and become insensitive to the noise, which means in our language that I would try to make these transition matrix elements small, and hopefully simultaneously I would try to make the derivative of the qubit energy with respect to relevant fluctuating parameters small as well. Strategy number 2 is the hard one, to actually tackle reducing the noise itself. And that is something that I certainly don't know how to do, because it will involve material science, all the dark magic of how you fabricate things and take care of surfaces, and some of it might be microwave engineering. So not a simple thing to do, but that would be the piece that directly influences what S of omega is, the strength of the noise at particular frequencies of interest. And then the last strategy would be active quantum error correction, right? So where you monitor for errors, you detect them in a very smart way that only reveals information about has an error occurred and what kind, but otherwise does not destroy any superpositions. And then once you have that readout, the syndrome measurement readout, then you have enough information to do a feedback loop where you correct the error, and then you repeat that scheme over and over again. Good. This was fairly general. Let's return to the question: is the transpon a good qubit when it comes to some of these noise considerations? And the first thing to remark, perhaps just historically, is that there's a circuit that essentially is the same circuit as the one that we've called the transpon circuit. It just operates in a somewhat different parameter regime. And that was the Cooper pair box, really going back all the way to 1998 and 1999. And that little circuit had a terrible pure dephasing time, somewhere of the order of just a nanosecond. And of course, when I say terrible, I should tell you with what timescale should we compare this, right? And well, that timescale would be how long does it take you to actually perform a gate? How long does it take you to read out the state? And that is, well, actually not even as short as a nanosecond. So this T-phi is really short. And I think looking at history, it's sometimes amazing how people didn't give up with when they saw how bad this dephasing time is. So it's good that sometimes you have to be stubborn and have hope that things can improve, and they did over the years. And so the transpon is part of that story. And so let's understand a little bit better how that goes. This 1 nanosecond, where does it come from? What is the noise that causes us so much pain when it comes to that circuit? So that kind of noise is called charge noise. And I'll try and explain a little bit what that means. I'm not going to even try to explain the microscopic origin, because that is not clear and not well understood, but I'll wave my hands a little bit and give you a general picture. So here's our circuit. You can call it transpon, you can call it Cooper pair box, and then this version I've actually grounded this lower piece of superconducting metal, and this upper one that is marked in yellow is floating, right? So this is the Hamiltonian that we've already seen for it yesterday. And now imagine that I might hook a gate voltage source to hook up to this piece of metal that is marked by some gate capacitance, right? And so now by changing the value of that voltage, I can actually shift the charge a little bit, right? So this operator n really counts the number of Qubit pairs. That's always an integer number, but by changing the voltage, I can actually kind of push the electron gas a little bit and sort of get fractional values, right? And this is represented by a slightly changed Hamiltonian, where you see I'm subtracting this this number ng from the operator n hat, and that ng it's called the offset charge, and it actually just encodes the voltage in a dimensionless way. So it's Cg times V divided by the Qubit pair charge. All right. One quick remark, perhaps. So this cloud is there because I noticed when preparing the lecture that, you know, our Hamiltonians are sort of falling from the sky in these days, and I find that a little bit painful. I remember when I first learned about this, I certainly wanted to know how do you get these Hamiltonians rather than somebody just tells you what they are. And just for reasons of limited time, I suspect that I won't get there. But just so you know, there is a systematic way to go from a circuit that somebody hands to you, maybe just as a drawing, and you can, in a completely deterministic and pretty simple way, derive the Hamiltonian. And that is known under the name of circuit quantization. And this reference here is one of the places where you can learn about circuit quantization in detail. It is worth pointing out that the quantization step is actually the kind of quantization that you all know. It is, in all cases, just as simple as replacing momentum by h bar over I, d by d, well, x or here phi, whatever your generalized coordinate is called. The thing that takes a little bit of work is, so how do you get to the thing where you make this replacement? So we actually want to derive a classical Hamiltonian first for a circuit. And so there's a little bit of thought that goes into, you know, we start with a Lagrangian. How do we actually get the terms into our Lagrangian? What do we consider kinetic and inductive, kinetic and potential energy? And then there's a Legendre transform. You get your classical Hamiltonian, and then the quantization is really simple. Okay. But since time is finite, we probably won't do that today or tomorrow. So let's see where we can get without going into that much detail. Now, I've described the circuit and this gate voltage source in a way that would indicate that I have full control over that gate voltage, right? So I'm the one who cranks up the voltage or lowers it. But the fact is that nature does a little bit of that by itself without me doing anything. And so the very hand wavy picture is, imagine that in the vicinity of the circuit, there are charges. Maybe they're sitting on the substrate, maybe they're sitting somewhere else, I don't know. And these charges can change their position. Maybe they hop back and forth between two positions, maybe it's more complicated. But due to these changes in positions, the electric potential of this superconducting island, marked in yellow, will vary, right? And so that is modeled in a way that might look like this. So this kind of noise has been measured a lot of times. It appears to be pretty close to a 1/f spectrum. And so here's now an example trace of that offset charge. And if you now think about what does that mean for the qubit, then, well, it means the following. If we plot our qubit energies as a function of this offset charge, then, well, we might notice that these energy levels vary a little bit with offset charge. So the black one is the ground state, this one is the first excited state, and those might be the ones that really interest us in using this device as a qubit. And if this offset charge has these random fluctuations now, that means that, well, we're going to get pulled back and forth maybe you've centered yourself here at some operating point, and once I take the fluctuations into account, we get these wiggles back and forth, which means that, well, the 0-1 splitting, the qubit frequency varies with time, right? And that is precisely the situation that we said is going to lead to dephasing. And charge noise is a pretty bad kind of noise. It's in certain ways, it's appropriate to call it strong. Oftentimes it bothers people more than flux noise. So what can we do about it? What have people done about it? And so to understand that, and indeed to understand how does the transpon and the Cooper pair box differ, let's take a look at what does this ratio of EJ over EC do to our spectrum. And so for that, I was planning to switch back over to my Jupyter notebook. Let's see whether we can make that happen. Here we are. And so this is now a plot that you haven't seen yesterday. It is energy levels as a function of this offset charge. And let's see, so right now I have a pretty large EJ over EC ratio of something like 33 divided by 0.6. And you notice that these low-lying energy levels actually vary very little with offset charge. And we can turn this around. So I'll make this EJ over EC ratio smaller, like this. And you see now things look pretty different, perhaps a little bit more similar to the plot that I showed on just the previous slide. Right now, we can tell that as I vary NG, all of these energy levels move, and in particular, the qubit splitting is going to change as a function of time. So these two regimes, large EJ over EC and small EJ over EC, are quite different from each other. And in fact, the Cooper pair box, the one that has this really small dephasing time, operates in this regime, which is also called the charging regime, where EJ over EC is small-ish. And the transpon operates in the, can I drag this back, operates in the opposite limit. And you see that levels are pretty flat there. And so I thought that instead of just showing you this, it might be nice to actually try and explain why this happens. So I'll spend a little bit of time on that. And the starting point obviously is Schrödinger's equation. We need to solve it in some way. So we'll write it down. There's the boundary condition that we mentioned last time. Wave functions need to be periodic. And well, a mathematician might tell us that, well, this is a known equation, and the solutions are special functions. They're called Mathieu functions, and the corresponding eigenenergies are so-called Mathieu characteristic values. And that is all fine and good, but it's not hugely helpful because these Mathieu functions are actually not that nice and well behaved, and in the end you have to calculate them numerically. And perhaps what we want to do is to get the more approximate but intuitive understanding, rather than to open something like Abramowitz-Stegun and see what we can learn about Mathieu functions. So let's do that instead. Let's look at asymptotic limits. So first, let's start with EJ over EC smallish. Actually, due to the 4 in front of the EC in our Hamiltonian, it doesn't have to be small compared to 1. Something of the order of 1 is already good enough. And in that case, our Hamiltonian looks like maybe it's worth a try to treat this EJ term, the Josephson tunneling term, perturbatively. And when I say perturbatively, that the 0th order, of course, is just drop it completely, right? Just get rid of it. And then we're left with just this first term. And recall the meaning of n hat. It's the operator that counts the number of Cooper pairs on the superconducting island. And of course, that number is integer. And it can be positive or negative, depending on whether you've added Cooper pairs to that island, or whether you've taken some out, right? The overall charge of that island can be positive or negative. And so with that in mind, we have the wonderful situation that our 0th order Hamiltonian without that perturbation is already diagonal in n, right? And what I see here is, well, if I plot these levels with respect to ng, it looks like a parabola, right? So for each integer value for eigenvalue of n, I get one parabola. I can maybe try and label those. So this guy here, is my pen active? 1 second. Looks good. So this is the parabola for the eigenvalue n equals 0. Okay. And then, well, there's another one for n equals, this is going to be +1 or -1. Anybody an opinion? Well, it's, I'm subtracting ng. I frankly I always get confused about that briefly because because the sign in front of the offset charge is more a convention rather than a deep truth. So we have ng minus, if I take this around, then this should be +1, I guess. Maybe there's a chance that I'm still getting it wrong, but you can check. And so now for every integer value of n, we get such a parabola. So if I've done this right, then this is the one for -1. And so they're all over the place. This is what this looks like. Which would indicate that, you know, at the ground state energy level has this funny behavior that it has these little kinks here. But if we just want to follow the lowest energy, then that would be our ground state energy. Whoops. And once we turn on the perturbation, so we actually treat this perturbatively, we will see that these crossings turn into avoided crossings, right? So now what was previously just parabolas opens up, and we get separate levels for the ground state and first excited state that don't really touch anymore. And again, you see that in this regime, we do expect the qubit energy to vary quite a bit with ng. And so we can, why is this there twice? There we go. So we can talk a little bit about important properties that are relevant when, well, both as far as dephasing is concerned, as well as this question of, well, how anharmonic is my qubit? You hopefully remember that without anharmonicity, when we just have a harmonic oscillator, it's nearly impossible to use this system as a qubit. So we want anharmonicity, but we want little charge dispersion, where charge dispersion is this quantity here that says, well, let's check out by how much this qubit energy can vary as the offset charges change, right? So we find the maximum of E01, we subtract the minimum, and well, the minimum would be here, the maximum would be here, and so that, well, if this was in, this is actually now normalized to E01, that's fine, but this charge dispersion is sizable, it's significant in the Cooper pair box. And likewise is the offset charge sensitivity, right? If I take a derivative of E01 with respect to offset charge, then in many places, in most places, in fact, this derivative will be large in magnitude. There are these special points which we heard are called sweet spots, where this derivative actually vanishes, right? At, for instance, at half integer offset charge, that's a nice point to work with. So yeah, let's say that these are large, which is bad for dephasing. But the anharmonicity is nice and large too. So here large is bad. That's the unhappy phase. This one is large. This is a happy phase, right? We like anharmonicity for qubit operation. And indeed, you can tell that the 0-1 splitting here is really small as compared to the 1-2 splitting. So that's nice. That helps us. I think next, I would like to switch over to the opposite regime. where EJ over EC is large. But before I do that, I'm going to catch my breath and also check the chat, whether there are questions. Maybe somebody has one. If you do, raise your hand.
No question so far.
All right. I never quite know whether that means things are going well or not. It's hard to see because you know, no faces, but hopefully one day we'll get back to normal. There's a chat now. Is there something now? I have one. What are the typical values for the NG noise? Very good question. So I can try and answer that in different ways. So one thing that you have probably already noticed on the previous slide is, as far as let's move my chat window here out of the way. As far as the energy spectrum is concerned, things are periodic in NG. It's actually a nice exercise, if you're looking for an exercise, to prove that directly from the form of this Hamiltonian, that whenever I add a full integer to my NG, I land back at the same energy values. Maybe the eigenstates are changed, but the energies are still the same. And so as far as energies are concerned, whether I'm in the interval between 0 and 1 or between 4 and 5 doesn't matter. Now, maybe your question is a different one, which is, during a certain amount of time, you know, how much does NG vary in total? And that's a question that I'll be more fuzzy on. So I do recall that in the few, there are not many experiments anymore that work with devices that are very charge sensitive. So in part, you're asking me about things that were actually investigated when I wasn't studying physics yet. But my understanding is that within, you know, the course of an experiment, within the course of a measurement, you will have variations of the offset charge of order 1, right? This sort of gets worse because there's actually additional jumps in NG of size 1/2, because if I have a quasi-particle, that corresponds to half a Cooper pair. And so whenever a quasi-particle enters the island or exits through the junction, then my offset charge will jump by 1/2. All right, there's more follow-up. As in, do we have to take into account the variance throughout all NG, or are we typically able to remain close to some nice NG point? Yeah, it's a good question. It really depends on, you know, over what's the experiment, over what time interval are you observing things. There are nice and more recent experiments. One I think by the Devoré group. There's also a different one from the group at Rutgers, and Misha Gershenson must be on the author list, where they monitor this offset charge over a long time, minutes, maybe even hours, definitely minutes. And you can see that NG varies quite a bit. They recognize these 1/2 jumps due to quasi-particles. So if you're interested in that, there's definitely more details to be found in one of these papers. All right. So next up was the Transpon regime, so large EJ over EC. In the warm-up question, we already mentioned that if we reinterpret the system or this Hamiltonian as describing a fictitious particle that moves in this cosine potential, then EC corresponds to 1 over the mass of that particle. And if EJ over EC is really large, then that can be interpreted as I have a really heavy particle. And if the particle is really heavy, then the situation is that I will get states that are far down here in the cosine well. So there will be quasi-localized states very close to the potential minimum. Okay, and saying that, we will be tempted, and that temptation is not all bad, we will be tempted to just say that, well, if only the minimum matters, then we're just going to do a Taylor expansion of the cosine around that minimum and see what we get from that. And that is indeed what people do. And there's several things to remark on that. I will do so in a second. But if I were to just, stop this expansion after the quartic term and throw out an overall energy shift that I don't care about, then this might be my Hamiltonian. And I hope that some of you look at this Hamiltonian and cringe and feel uncomfortable because this Hamiltonian has no bound states whatsoever. This quartic term comes with a negative sign, and ultimately it's going to take over. So we have to explain a little bit better what kind of approximation this is actually supposed to be and how this is supposed to work. First of all, what I've done here is not ordinary perturbation theory, right? Expanding a potential around a minimum, that's not really how perturbation theory works. And what makes this even more subtle than other cases is recall that we said our boundary conditions are periodic. But once I do this expansion, so let's suppose I stop after the parabolic, the phi square term, right? Then the potential I have is confining. And certainly I can't use periodic boundary conditions anymore. So this harmless looking expansion of the cosine around its minimum fundamentally changes the boundary conditions. It's also clear that this is only going to work for low-lying wave functions, right? We saw last time that there are actually wave functions that are above the cosine well. Perfectly fine wave functions, but they will not be well described by modifying or approximating the potential in this way. And as I mentioned, this quartic term, I can only treat that with care, and in our case, care will mean that I'll only consider it as a perturbation, and in some cases I will have to specify that we will truncate our Hilbert space so that I don't get myself into trouble. So all of this sounds a little bit fishy, but it's not too fishy, and it's super useful actually. So bear with me, and we'll come hopefully to a conclusion that this way of treating the transpon in this regime is actually quite beneficial. Good. On that, the first point to recognize is that these first two terms now look pretty darn close to just a harmonic oscillator, right? It's momentum squared, and then there's the position squared, so that looks good. The one thing that could bother you is this minus ng. It stands in a position that smells a little bit like vector potential, but it's strange because it's constant. There are special things that happen for a particle on a circle, which actually make a constant vector potential important. But here, since we've switched our boundary conditions to just the, oops, there's a space missing, I apologize. We switched to regular boundary conditions that just are, wave function goes to 0 at plus minus infinity so that we can normalize it. And with that switch, we can actually eliminate that offset charge exactly from our Schrodinger equation, from the Hamiltonian. And that offset charge within this approximation plays no role anymore going forward. And that means we really have a harmonic oscillator. It doesn't just look like one, it is one. So we'll introduce ladder operators in the usual way, where our phi here is going to be proportional to b dagger plus b, and our n operator is going to be proportional to ib dagger minus ib. And if you want another little exercise, then make sure that you understand how to go from these coefficients in our two harmonic oscillator terms to expressions like that, right? I'm pretty sure that for a particle with mass m, you know how to write down the oscillator length in terms of h bar and m and omega, and you know how to write down omega in terms of the coefficients appearing in the Hamiltonian. But it might be good if you're not immediately confident how to do this in this case to, well, here this thing is called 4EC, nothing to do with h bar and m, and this is EJ, so see whether you can derive both the oscillator length and the oscillator frequency. Okay, but I'm sure you can do that. And once you have, this is what the Hamiltonian looks like, right? Here's my simple harmonic oscillator. The oscillator frequency is 8EC-EJ, square root of that. Some people might recognize that as the plasma oscillation frequency, but for us, that's just a name. And then this last term here boils down to something that looks like B dagger plus B to the power 4. And I wonder, no, I don't wonder. You might wonder whether I made a little boo-boo here, because it looked like EJ up there, and now I'm claiming it's EC. But if you take good care of these prefactors, you will find that there's in fact no mistake. And I'm again remarking over here that we need to treat that perturbatively and not worry about the fact that it's still a quartic potential that, strictly speaking, does not allow us any bound states. Good. And so there's one further approximation which comes directly from this idea of treating this quartic term perturbatively. If you do so, then perhaps one starting point would be to let's just multiply this out, right? So it's B dagger plus B to the 4th power. We should get a whole bunch of terms that all have 4 operators and some combination of B daggers and B's. And if you consider leading order perturbation theory, you will immediately find that only those terms matter where you have just as many B daggers as B's. So there are a bunch of terms that in leading order perturbation theory can be dropped. And if you drop them and keep the rest, then you can rephrase this Hamiltonian in this form, where we've absorbed actually a lonely B dagger B term from this game into h bar omega q. So this guy is not quite square root 8 EC-EJ. It's actually square root 8 EC-EJ minus EC. I can write that down. So that's square root 8 EJ EC minus EC. And then this term here is our anharmonicity. Some people would say that this is a self-Kerr interaction. And this, by the way, can be also written in the form 1/2 EC times n minus 1 times n, where n in my notation here is B dagger B, right? So it's an interaction term. It does nothing if your excitation number is 0 or 1, right? Because in that case, this excitation doesn't interact with anything. But as soon as I have 2, this term becomes active and shifts our energy levels, and in fact shifts them in a very, very simple way, which is shown here over on the right. So our qubit splitting between 0 and 1 has this frequency omega sub q. And then the next one is smaller by an amount EC. And the next one is smaller by another minus EC. And that means that we have an anharmonic spectrum. That is good, but we'll probably have to talk a little bit about how is that anharmonicity large enough. So just as for the Cooper pair box, the charging regime, we can talk about charge dispersion and offset charge sensitivity. And we saw that in our current approximation, there is no such thing, right? Within our approximation, NG plays no role whatsoever. it has completely dropped out. And so no charge dispersion, no offset charge sensitivity. If we were to work harder and do an approximation that would actually involve thinking about tunneling of the particle, well, I shouldn't say from one well to the other, because the particle lives on a circle, so it basically tunnels across the whole circle back into its very starting position. So if we do something more sophisticated, then we would find that this charge dispersion is exponentially suppressed. Since it has to do with tunneling, exponential suppression is not too surprising. And this atomicity, well, is smallish. And if I draw my happy face versus sad face, then this one is very happy, right? Small atomicity is not happy, because we might worry that this thing cannot be used as a qubit at all. But it can. And I'll say why in a moment. This is just another overview, once again, now showing plots of the energy spectrum as an overview here for a smallish EJ over EC value, some intermediate one, and one that is clearly in the Transpon regime. And you see these properties: large atomicity, but also large charge dispersion. This is our intermediate case. I'm not going to say anything, but here we clearly see that levels are fantastically flat with respect to offset charge, but it looks pretty darn harmonic, right? I don't know whether with your eye you can tell that these two splittings are not the same. What's nice is that the atomicity doesn't vanish as quickly as the charge dispersion, right? I did mention that the charge dispersion goes down exponentially. Here's the exponent. It's actually well, it's a square root EJ over EC in the exponent. And so in a log plot that looks like this, charge dispersion becomes small very, very quickly as you increase EJ over EC. But the atomicity, well, if you talk about the absolute atomicity, that's always EC. But in many cases, it's the relative atomicity that counts. So I'm going to divide the absolute one by the actual qubit energy splitting. And that, well, that does approach 0, but it approaches 0 slowly, right? This is an algebraic expression where, well, it goes like 1 over square root of 8 EJ EC, right? And you can see how this approach looks much more benign than the exponential scaling here. And that is what rescues this idea of using the large EJ over EC regime due to the difference between the square root scaling and the exponential scaling. There's a nice wide parameter regime where you have basically no charge dispersion. You're very well protected from charge noise, but atomicity is still good enough so that you don't have to worry about using your circuit as a qubit. Good. Any questions at this moment?
Yes, Jens, there's one in the chat.
Excellent. How can we tune the EJ? Is that related to the momentum of the transpon, so on its dimensions? Good question. It's, at least in my language, it's not related to momentum. So the way I interpret this, let me switch to a place where we have the Hamiltonian in its original form. Right. So momentum, I would call this the momentum, and so this is in the kinetic energy term, which is associated with the charging energy. EJ is out there in the potential energy term, and there are two distinct ways in which you can change EJ. One is at the moment of fabrication, and one is if you do something a little bit more interesting, you can also do in situ tuning. But if we ask about how do I choose EJ at the moment of fabrication, that's all about, well, what's the size of your junction, and what's the thickness of the oxide layer. Right, both of those affect the IC, the critical current. In aluminum oxide junctions, because the oxide layer is self-limiting, my understanding is that this oxide layer always ends up to be of pretty similar thickness, unless you do something unusual. But you can vary the area of the junction, and larger area junctions will give you a larger EJ. Good. In situ, I will talk about that actually in just a moment, because in the next section I will sort of talk a little bit about a slightly more general version of the transpon that has two junctions rather than just one, and I'll also talk about other kinds of superconducting qubits. So just wait for a moment. If your question really was in situ tunability, I'll get to that. No more questions? You sure? You're welcome. All right, then let's do this. So back to where we ended, which was here. And so the next section is on flux-tunable transpon and other superconducting qubits. Again, if you're following or using this review of modern physics as our companion, then that will be sections 2E and 2F. And in fact, instead of going through the math steps that you will find for the flux-tunable transpon in that paper, I thought we would do this more visually and skip some of the math, just so that I don't run out of time too early. So SE Qubits has multiple qubits inside. You can tell, right? All these buttons have different qubits labeling them, and so tunable transpon is one of them. So we immediately get something that looks quite different. But first, let's actually open up this qubit info thing, and you get some information. Let me try and zoom in here a little bit so you can see, right? So the circuit is similar to the one we considered before. In fact, if I were to just remove this junction here on the left, then that is our transpon circuit. But now we have these two, and they form a loop. That loop is also called a squid. It's a DC squid. And if you go through the math, you will find that threading a magnetic flux through this loop. So you switch on a magnetic field, and some of that field will penetrate this loop. So we get a magnetic flux. That magnetic flux will essentially give rise to an effective Josephson energy that is flux tunable. So the expressions are in fact here. At the end of the day, when all the dust settles and you've used a little bit of addition theorems and trigonometry, the two junctions actually just zip down to one effective junction term, but the EJ, the Josephson energy, is now dependent on this magnetic flux. And the most general expression looks a little bit cumbersome. This includes the potential complication that these two junctions don't have to be identical. If they're identical, then this simplifies a bit. But the main message is that this is what people oftentimes do if they want to be able to tune their transpon in frequency. So I believe the Google processor has flux tunable transpons. Flux tunability comes with a price that you're exposed to 1/f flux noise. So there's some trade-off in convenience of tuning versus, in some cases, limiting T phi from flux noise. Okay, so let's briefly look at this. So this plot now, and I'm going to zoom out a bit. There we go. This plot now looks quite different from what we saw before. It should, because now we're plotting energy levels as a function of the flux, not some offset charge. So this is now the magnetic flux. And if you're an experimentalist, you will probably tell me that you don't like this plot because you cannot measure an absolute ground state energy. All you can measure are transition frequencies or energies. So let's subtract the ground state energy. Then this looks like such. And right now, I have this D parameter is sort of the difference between the asymmetry between these two junctions. I could switch this off and levels change slightly here, so it becomes actually a bit simpler. But the important message is that indeed, by changing the magnetic flux, you can go from your original qubit splitting here at at 0 or at 1 flux quantum to, in this case, 0 splitting when the flux is exactly half a flux quantum. If there's asymmetry and in real life there is, then that's not quite 0. Okay, so that's a flux tunable transpon, and yeah, as I said, that's pretty much a way to change at least an effective EJ in situ. All right, and then I was supposed to also say a few things about other superconducting qubits. I like other superconducting qubits a lot. In fact, in the last couple of years, I've worked very little on Transpon. I think they're nice. People like them and use them, but they're sort of boring at this point. And it's to me, it's quite interesting to think about, are there actually better circuits that perform better than the Transpon? And it's an interesting question. The Transpon has been around for a long time. It has been optimized over the years. And so I think there's a good chance that if you give a different circuit a little bit of time to be optimized, then maybe a different circuit actually performs better. So there are ideas about protecting circuits better from noise, for instance. We could look at least one of them. I really like fluxonium. Looks different. It actually has a large inductance, which we didn't find in the Transpon. This inductance wants to be so large that in the experiment, it's actually built by using a Josephson junction array. But the model of just replacing this in our calculations by a very large inductor is very good. And so it's a single junction shunted by an inductor. If I were to go through circuit quantization, I could derive that this is the Hamiltonian. And you see that this qubit, that fictitious particle, if you will, lives in a different kind of potential. There's still a term from the Josephson junction, right? That's our good old cosine. But there is an inductive term with a parabola on top of that. So if I switch over to looking at wave functions, then you see that indeed there's now some parabolic background overlaid on the cosine potential, right? So fluxonium has wave functions that look quite different. There are a number of interesting and very different regimes depending on, well, EC, EJ, and EL. It's a little bit richer. There's not just 2 energy scales. That makes life more exciting. And so we could talk about fluxonium a lot. I don't think I will, but if you're interested, I encourage you to check out this package, and you can play with it. And if you have questions, I'll be happy to answer them, of course. Good. Back 2 slides. Slides not there. And so next chapter, important chapter, is light matter interaction in circuit-QED. And the motivation for thinking about that is, so far, all I have described is a lonely qubit by itself. I haven't explained how I would try to manipulate its quantum state. I haven't talked about how I would read it out. And the answer, especially for something like the Transpon, is Well, we'll couple that circuit, that qubit, to a harmonic mode. And that harmonic mode could be a lumped LC circuit. Some experiments do that. It could be a mode of a 2D transmission line resonator, or it could be a mode of a 3-dimensional resonator. And those 3 cases are indeed represented in some of the nice figures that you can find in this review of modern physics. So here's the 2D case, where the transpon sits smack in the middle of this transmission line resonator, where just so that we're on the same page, this here is the center pin of this transmission line resonator, and then the pads here and here are the ground planes. And you see that the transpon is strategically positioned such that it sits where the electric field or the voltage, if you will, has an antinode, right? So it will couple to the electromagnetic mode in that resonator. The 3D case is similar conceptually, but different in some ways in how we need to model it in detail theoretically. But at the very basic level, it's the same story, right? We now have in this case, cylindrical cavity with a little pin down there. And there's a mode, there's several modes, of course, in such a resonator. And the transpon qubit gets inserted from perhaps the side, as shown here, and it basically acts like a little antenna that through these metal pads, it's like a big dipole that couples to the electric field, right? That's the nature of the coupling. And then finally, here's the lumped element example, which has sort of 2 sides. Side 1 is in many cases when your modes in your 2D or 3D resonator are nicely separated and the qubit is close to just one particular mode, then this lumped element circuit here is actually a good model for the more complicated system. And then, as I said, some experiment actually use lumped elements LC oscillators. So this could also be an actual physical system. And so you see what we've got indeed is the transpon circuit as you know it, and then an LC circuit, and the 2 are capacitively coupled to each other. And if we now ask ourselves, well, what does that look like? What is the interaction? What is the full Hamiltonian for that system? Then again, the nicest way to go through this, because it's systematic, I would say, is a circuit quantization. But if you allow me to wave my hands just a little bit in between, we can again circumvent that. So the first Hamiltonian, right, should look very familiar by now. It's the Transpon Hamiltonian, our good old friend. And then H sub R, I think I'm trying to use notation from the review of modern physics. This R probably stands for resonator, and the resonator mode of interest is represented by this LC. And well, the LC has a charging energy E sub C R, and it has an inductive energy E sub L. And so you recognize it's a phi squared N sub R squared term. And yes, that's a harmonic oscillator. But what about the coupling? Well, this is where we wave hands a little bit, but not too bad. So recall that we previously had a Cooper pair box with a capacitance, a gate capacitor, and that led to this offset charge Ng if instead of this LC oscillator, I put a gate voltage source, right? And so now instead of the gate voltage source, we actually have the voltage across the LC oscillator. Or in fact, what we couple here is the charge, right? We phrase this in terms of offset charge. And so the offset charge now is replaced by the charge associated with the resonator capacitor. And if you do this carefully, you'll find that this gets slightly modified. And indeed, the C sub G, our gate capacitor, makes its appearance, which is comforting because that is indeed the thing, the element that produces this coupling here. And yes, this is hand wavy, and if you're seeing this for the first time, how should you have come up with it? I do encourage you, if you're interested, look at circuit quantization, and if you have questions about it as you do, I'll be happy to answer those. Good. But so we'll follow this somewhat non-rigorous route, and we'll just say that, all right, if this is the game, then we'll stick this back in and it'll replace NG. And now we have a new Hamiltonian that includes the coupling, right? So this coupling comes about as soon as I multiply out this term, right? I will get a cross term where n hat, which is the charge for the transpon, gets multiplied by n sub r, which is the oscillator charge, right? And so I can do that. And I'm actually doing two steps at the same time here. I have multiplied this out, and I've introduced some new names, as well as switched back over to ladder operators, right? I know that this harmonic oscillator Hamiltonian for the resonator in the end should boil down to something as simple as this. So the oscillator is getting A's and A daggers. And then the transpon keeps its B's, right? This was the harmonic oscillator approximation for the transpon. Here's the negative anharmonicity that we derived. And then the cross term, that cross term is, well, it was, we said N and R. So here's N up to a factor of I, or yeah, and here's NR. So this indeed is our interaction. And what is the interaction strength? There's a number of different interesting forms to write that down. For now, let's just do the simple thing and note that once I do multiply this out, I get a ratio where in the numerator I still have C sub G. Since EC appears here as a prefactor, it's actually in the end not just a bare resonator capacitance that goes into the denominator, but a combination of that with the gate capacitance. So this is a sum of two capacitances. And then it's the 0-point fluctuations for the qubit charge and the resonator charge that enter this coupling strength. In typical circuit QED experiments, how do energy scales compare? So typical experiments would choose harmonic mode frequencies of the order of a couple gigahertz, maybe something between 3 and 10 gigahertz. Likewise for the qubit frequency. And this coupling is small compared to that. So in 2D, in the 2D architecture, G's between tens and hundreds of megahertz would be standard. And so we're looking at a Hamiltonian where this interaction strength is small compared to the bare frequencies of the two subsystems. So that's good to know, and that will immediately allow us to simplify this interaction term somewhat by using what some of you hopefully have heard of before, rotating wave approximation, which is going to drop the terms that pair up to raising operators and to lowering operators. If you think about a procedure where you were to treat this interaction perturbatively, it's clear that those terms are going to lead to a subdominant contribution, and so dropping them is a nice simplification. So what we are left with is something that looks like H bar G, B dagger A, and the Hermitian conjugate is B A dagger. All right. So that's an interesting overall Hamiltonian. First comment to really keep in mind is if I were to eliminate this anharmonic term, which came from the Josephson junction originally, even though after a lot of manipulation, it now comes with EC, but the origin of this term is actually the Josephson junction. Without that term, everything is actually linear. And we could exactly diagonalize this. Everything is just coupled harmonic oscillators and life is boring, right? So this, again, this anharmonic term is crucial for this to work, for the qubit to be a qubit. And so we'll have to really make sure we treat this term properly. I think the strategy that the review of modern physics suggests we first consider is actually to look at a slightly different limit. So I think I have the next slide should be empty. There we go. So the model that we've looked at, Transpon plus harmonic mode, that one is weakly anharmonic. Okay, and then the system or the model that is much simpler, which we should make sure that we all understand. So I will go through that, probably not in full detail this time, but in full detail next time, is the Jaynes-Cummings model. Which consists of a two-level system and a harmonic mode. And I want to argue that this is the opposite case in the sense that this is like having infinite anharmonicity, positive anharmonicity. Why do I say that? Well, so case number one over here, let's enumerate them. Case number one, the transpon, again, remember its spectrum sort of looks nearly harmonic. I'll exaggerate it a little bit so it's clear enough. All right, and then there are more levels. The two-level system, well, it only has two levels, but I can interpret that in a way that says, well, maybe there was a third level, but the anharmonicity is so large that I've shifted all that third level and everybody that is above out to infinity, right? So that's why two-level system corresponds to really large anharmonicity. And that Jaynes-Cummings model is a beautiful model that is very well known in atomic physics. It's exactly solvable. And so for that reason, there's a lot of intuition and insight that we can gain by studying that model first. And I think my timing is slightly off. I think I'll probably end here a couple minutes early, but that's all right. We will at least write down the Jaynes-Cummings Hamiltonian, but I don't think I'll start discussing the solution for the Schrodinger equation in these last couple minutes. So Jaynes-Cummings Hamiltonian. The Jaynes-Cummings Hamiltonian is such that there is a two-level system. I might write it as 1/2 omega q sigma z. And there's and I hope you will forgive me that in my world h bar is usually 1. If that concerns you, then I'll try to insert it back, but I might forget to write it in some places. So I hope you can forgive me. And then the harmonic mode is still there, so I'll write that as h bar omega r a dagger a, and then in a very nice way, the Jaynes-Cummings interaction mimics the interaction that we just saw for the A's and B's in the case of the transpon. So we would write that as h bar g a dagger, and now the B lowers the state of the actual transpon. Here it's in a two-level system, so the operator that lowers my excitation state would be sigma minus. Except I think this is a mistake I I've seen in various places, and maybe I'm repeating it right now. If we use the standard definitions of all the Paulis, then I think I will need to introduce a negative sign in front of my very first term here. Alternatively, which is actually notation I prefer, I could write this as h bar omega q, sigma plus, sigma minus, just like a dagger A or b dagger B. That's only a constant shift relative to the notation in terms of sigma z. All right, but finishing the interaction term here, we'll end with a sigma plus. And so that is the Hamiltonian that we'll study next time. The interaction is of an interesting form. And in fact, the simple form of the interaction is crucial for the fact that the Jaynes-Cummings model can be exactly solved. We can already mention, right, that the kind of process that this interaction describes is the following. So if I look at the first term, what does it imply? Suppose that my qubit is currently excited. Then what applying this term to my state might do is remove the excitation from the qubit, right, and transfer it into the harmonic mode. And then the second term does the opposite, right? For that one, I might consider my qubit in the ground state, and what happens is an excitation is taken out of the oscillator and transferred over to the qubit, and the qubit gets excited. And we'll see that this simple form is nice because this implies that there's an interesting conserved quantity. And as you may remember from your quantum mechanics 101, conserved quantities typically help us find the spectrum of our system in a simpler and more efficient way. And in this case, this goes all the way to ensuring that the Schrodinger equation has exact solutions. So we'll discuss that next time. Yeah, I'm just 4 minutes early, but that's all right. Maybe there are actually questions from some of you.
Thank you, Jens. Any question? Yeah, Julia.
First of all, thanks for...
What time is in Russia?
Oh, it's almost 9.
Okay.
So
thank you,
yeah,
thank
we are not far away from Rome, but quite far away from Fermilab.
Thank you for the commitment. Right.
Thanks. First of all, thanks for really nice lecture. I just was reading this review, and you made some points really clear, and that's really cool and nice. And returning back to point of G interaction. So as I noticed, you said it depends only on 0-point fluctuations. So there are always kind of 0-point fluctuations, but there is interesting fact connected with it. So how we could describe physically their presence and this constant. I don't know, am I okay with question, but it's...
Yeah. I think, yeah, I was a little bit vague and lazy when it came to that. So as you mentioned, the review actually gives 2 alternative full expressions, right? I only even wrote down something that had a proportional sign in it. So we can briefly look at those expressions and see what we can learn from them. I just need to find my right page here. So I have one already over here, and then the other one is on the other side. Yeah. Okay, so there's a I checked actually one of these expressions this morning, and it's a little bit of just algebra. So if you don't see immediately why it boils down to the following expression, then welcome to the club. I couldn't see it immediately either. But what you find is that this G, one interesting form is you can relate it to your resonator frequency. The ratio of the gate capacitance, which produces the coupling, and the sum capacitance. And then the factor that is the 0 point flux this is the factor for the 0 point fluctuations of charge. So this is EJ over 2EC to the power 1/4. And then the rest is sort of separate and written in this nice form as the impedance, the characteristic impedance of the oscillator or of the harmonic mode, divided by what some people call the vacuum impedance, and then a square root of 2 pi and alpha, where alpha is the fine structure constant. So that looks exciting. It's written in this way because the characteristic impedance of your oscillator in most experiments, it's sort of in the same range. So that is not going to change that much. The vacuum impedance is a constant of nature, so is the fine structure constant. So it's the terms in the first line that tell us something about the actual coupling strength as we can try and vary it. And so you see that the thing that the two things that you can try and manipulate is you can make the coupling strength larger by increasing the EJ over EC ratio. And that comes at the cost of making your transpon even more harmonic. You could play with the resonator frequency, but you probably don't want to go too far away from this range of a couple of gigahertz. And you can play with the gate capacitance to some degree. And so that writing G in this form is maybe a little bit nicer because you get more insight into what can you change in the experiment rather than me just saying that, well, there are 0 point fluctuations and but how do they relate to actual parameters? This expression shows how they do.
Yeah, thanks a lot. Yeah, it looks nice, clear, and really fundamental. To be honest.
Yeah, I guess whenever we can write something that involves the fine structure constant, people are in awe. But it's really it's not too surprising that it shows up in some form because, well, it is what governs the coupling between charges, electric charges, and the electromagnetic field. So it's actually good that it pops up here.
Thanks, cool.
Thank
And
you.
then-
There's a question in the chat. No stupid questions.
There are no stupid questions. That's right. All questions are good. We were doing everything with bosonic operators. Yes, that is right. But we want fermionic modes for quantum computing. No, we don't. How does that work? We do not need fermionic modes for quantum computing. In fact, how would I notice whether a two-level system is fermionic or bosonic? Well, it all has to do with permutation rules and interchanging positions of two particles, but I'm not ever going to exchange positions of my qubits. They're patterned on a chip, that they don't move. And indeed, all that I need for quantum computing is a two-level system. Whether you make it bosonic or fermionic doesn't matter.
Sorry, can I have a so I mean the question was because obviously James Cummings Hamiltonian has a two-level system which is fermionic because it has spin operators, right? I don't know how to even say that because if you could say that everything that looks like spin 1/2 has to be fermionic. But many of the systems that we use as qubits are not two-level systems, right? Every superconducting qubit has higher level, and there's nothing fermionic about them. Okay. Thanks.
So I fully agree that we learn and know and appreciate that if we have a true spin 1/2 and we're talking about a single particle with that spin, then that particle
is fermionic. I fully agree with that. But all we need for quantum computing, we don't need to work with individual particles. As long as we're careful that we don't have quantum amplitude leak into higher levels, we also don't care whether there's a level or 2 levels or 3 levels above, right? And so for that reason, the nature of are you a boson or are you a fermion is really not crucial for quantum computing.
Okay, because I was kind of under the impression that, so yeah, I do realize there's this, how is that called? Continuous variable quantum computing or something like that, that's bosonic. And I was kind of under the impression that those 2-level systems, I don't want to say require, but usually are written in terms of fermionic operators, right? But looking at it now, I guess that's not necessarily the case.
I mean, I would claim that when I write down, now I have lots of feedback. When I write down an expression where I have qubit number 1, and I have qubit number 2, and I start asking about some interesting commutation rules, then they really don't care about each other, right? I can think about exchanging them, but really they're 2 separate subsystems, right? And it's very different from permuting 2 particles.
So I don't think I'm talking about multiple qubits. I'm thinking about a single qubit. So it's
but hang on a second. So if all I have in the world is just a single particle, how would I figure out whether it's a fermion or a boson? I mean, I sure I can again measure some angular momentum if I manage to. Our qubits certainly don't have angular momentum, and there's no, with a single particle, there's nothing to permute.
I mean, yeah, you're right. It's Hamiltonian with fermionic operators. That's my answer. But
well, tell me, in what way is Pauli Z a fermionic operator?
Yeah, I see. Yeah, that's true. Yeah, maybe I was thinking about it like that in the wrong way, because like you have a 2-level system and like it's, I mean, a bosonic, yeah, I don't know. I'm kind of confused right now. I guess you could populate it with many particles in the 0 level and many particles in the 1 level, and that kind of confuses me at this time. But
we don't populate with particles, right? When I talk about a qubit or a superconducting qubit with multiple levels, and the thing that I fill into levels is not particles; it's just probability amplitude.
okay, yeah, sure. It's a harmonic or an unharmonic oscillator, and like it has its modes. But couldn't you say that those modes are populated by something?
By excitations, sure.
Yeah, sure. Yeah, okay.
I can have 1 excitation, I can have 2 excitations, I can have probability amplitude in multiple levels, but it's not the many body system or a simple model of a metal where I place particles into levels. That's not I think that's not quite the right picture here.
Okay, thanks.
Mm-hmm.
There is one question from Salvatore.
Is there a formula for the light matter exchange rate, and how does it affect quantum computation? So that rate, at least at the single excitation level, is this G. That is precisely what governs that rate. So if you, we'll see next time that if you place the 2-level system and the resonator at the same frequency, so the 2 subsystems are on resonance, then if you were to start the system in a state that is not an eigenstate, namely let's pick the state where initially the qubit is excited, but the oscillator is in the ground state, so no photons, no excitations, then you will periodically slosh back and forth between having that excitation sit in the qubit and then having the excitation sit in the oscillator, and back and forth. And the rate for that is G or maybe 2G. I have to think about the factor of 2. The splitting is 2G, that much I know, the vacuum Rabi splitting.